Here are some instructions to help you with Lab 10, Earthquakes and Tsunamis. And I've placed on the bottom of this slide that this lab addresses the Unit 4B level outcome number 6, which is name the types of seismic waves, their manner of propagation, and how they can be used to locate earthquake epicenters. And that is what this lab is all about, is locating earthquake epicenters and also looking at tsunamis. The lab is rather long, and so I'm probably going to wind up dividing this into 2 videos. I hope it doesn't wind up going into 3, but I want to get all of the explanation in there that I can. So the key thing here to know is that different seismic waves that are created by earthquakes travel at different speeds. And shown here are 4 types of waves. P waves, which are the fastest, S waves, which are the second fastest, and then some other waves down here that we're not going to worry about because that's not useful for helping us find out the distance or the location to an epicenter. But this fact right here, that these 2 waves are generated at the time of the earthquake, but they travel at different speeds to the recording station, is going to be very crucial. So how do we find the epicenter? Well, the P wave, as I mentioned, always arrives at a station first, and then the S wave. So if you look at this little cartoon down here, you see an epicenter of an earthquake, and then in green, they're showing the P waves, and in red, they're showing the S waves. And so the P waves arrive first at a recording station, and the S waves come later. Now, the farther the station is from the epicenter, the later the P wave will get there, and the more time there will be before the S wave gets there. So let's look at this over here. Station 1 records the P wave before station 2 and before station 3. This is time going from left to right. And that makes sense. It has a farther distance to go. But also notice that the time between the P and the S wave increases. So up here at station 1, it looks like there's about a 5-minute delay between the arrival of the S wave from the P. At station 2, there's about a 10-minute delay. And down here at station 3, it looks like there's almost a 15-minute delay. This information can be really useful to figure out how far away the epicenter is, because what we get when we're looking at station data are these things right here. We don't know how far the epicenter was, but we can use this to kind of go backwards and figure out our distance to the epicenter. This is kind of like what happens with lightning and thunder. Lightning is static electricity, and when lightning occurs, it travels at the speed of light. It's light, which is so fast that if lightning flashes 10, 20 miles away from you, it appears to be instantaneous. Thunder is the sound that lightning made. So it's generated at the same time as lightning, but it travels at the speed of sound, which is much slower than the speed of light. So if a storm is close to you, the lightning will be followed by the thunder in about 2 or 3 seconds, which sort of corresponds to 2 or 3 miles. Now, when I was a kid, this is what my mom taught me to do to figure out if a storm was approaching or leaving the area. If you counted the seconds between the lightning and then the corresponding clap of thunder, and let's say you counted to 5, well, then we would say, okay, the storm is 5 miles away where that lightning is being generated. If the next lightning is followed by thunder only 3 seconds later, then we would say the storm is getting closer to us, because that separation between the lightning and thunder timing is closer. On the other hand, if the next flash of lightning occurs and we count to 8 until we hear the thunder, then the storm is maybe 8 miles away and it's getting farther from us. So it's the same exact kind of analogy for P and S waves. They have a set speed, and we can look at the difference between when they arrive at a seismic station to tell how far away the earthquake was. What we do is we take those times that are on the seismograms that I just showed you. Let me go back. This time right here of maybe 5 minutes or 10 minutes, we have to be more precise. And then we come to the time travel curve, and this can be somewhat challenging, but let me walk you through it. So on the bottom, we have the distance from the epicenter to the recording station. So if you're at 0, you are right where the earthquake occurs. If you are here, you're 2,000 kilometers away from where the earthquake occurred. on the axis over here, we have travel time in minutes. And then we have these two red curves labeled P and S. So let's start with the P. The red P line represents the speed of the P wave, basically. So if you are at the earthquake epicenter, the P wave arrives instantaneously. If you're 2,000 kilometers away, then it took about 4 minutes and 6 seconds, that's what this means, to arrive, right? It took time for that P wave to get to you. It's not instantaneous. If you're 4,000 kilometers away, it took even longer. It took 6 minutes and 58 seconds, etc. So the farther you are from the epicenter, the longer it takes for the P wave to arrive. And the same is true of the S wave. Now the S wave's curve is above the P wave because it's slower. But what I really want you to notice is the gap between them. So here we have a gap of, I don't know, about 3 minutes between the arrival of the two waves. As we go farther, the gap here is about 6 minutes, and the gap here is about 8 minutes. That's the S minus P time, the time between the arrival of the two waves. Now normally, we don't know our distance. What we know is this time. And so we use the time to figure out the distance. Okay, and so and I'll go over that again in a minute. But once we have our distance, then we can plot on a map the radius to the epicenter. Let me go back. So for this recording right here, we know we're 2,000 kilometers away from the epicenter, but we don't know what direction. So we would draw, if this is our station, we would draw a circle with radius 2,000 kilometers. Somewhere on that circle is the epicenter. If we had another station, station 2, that recorded it at 4,000 kilometers away, then we could draw a circle around station 2. And you can see those two circles intercept in two places, up here and down here. So we need a third station, which is station 3, to record and see where all three intercept. And that is the epicenter. Now, if you watched learning video 4B.2, you'll remember that beginning at around the 14-minute and 50-second mark, the narrator talks about this exact same thing. She shows you a seismogram image with P waves and S waves identified, and the time between them is 24 seconds. Then she shows you a time travel graph with the P and S waves. There's a third line here, S minus P. Don't worry about that. And what she's done is she's taking a measurement here from this scale of 24 seconds. That bar represents 24 seconds. And you move it along until you find a place where the P and the S wave are separated by 24 seconds. And again, I got that 24 seconds from this. And when you get it, you drop down and you read the distance. So in this particular example, this seismogram tells us that the earthquake epicenter is 240 kilometers away. Again, we don't know the direction, but if we have multiple stations recording the same earthquake, we can triangulate. And so that's what's shown in the next part of her image. She's got 3 different stations here, and she's showing how all 3 of them intersect at this red X. So the other thing we're going to be talking about is tsunamis. And tsunamis are generated when earthquakes occur underwater, especially subduction-related earthquakes, which makes some of the ground go down and some of the ground go up under the water. So this is showing some displacement along a fault, which generates an earthquake, and that water above it is going to respond to that change at the seafloor, and it's going to generate a wave. Now, in the deeper areas, the waves go very, very quickly, 800 kilometers an hour. But they also have a very small wave height, which is the amplitude. And their wavelength is also very long. It's very far between crest and crest. So people that are out in the deep water might not even notice a tsunami. And so in order to identify tsunamis when they happen in deep water, we have instruments such as this here, which is a tsunami recording buoy, which then relays the information back to a tsunami warning center. Now, when these waves approach the shore, they start to grow in height because they're sort of bunching together. You notice their speed is slowing down. And so the water has nowhere to go but up. And it goes up, and then when it gets to this shallowest area, then it becomes very obvious that it's a tsunami. So the tsunami we're going to be talking about is a real event that occurred in December 2004 in Sumatra. And here are a few images. This is a boat that's been brought inland several miles from the shore. Here's a photograph where some people are near the shore and the water's coming crashing in and they're just about to start running. So that's what we're going to look at in this lab. One other thing that happens, which is unusual, but it's a feature of tsunamis, is that as the wave arrives, the first crest, the water actually recedes back before it comes forward. And when this happened in Sumatra, lots of people went down to the beach because this maybe happened over 20, 30 seconds or 40. And they were like, oh, look, there's fish plopping around and there's, the water's out, not knowing that what was coming next was this huge wall of water. Okay, so let's get to the lab. The first part is learning how to locate an earthquake epicenter. And there are some errors on the page numbers because the pages have been reformatted since the last one. So I've shown those corrections here. So the first thing you're going to do is you're going to look at seismogram records of the main shock of this earthquake in 2004. And we're going to try to figure out where the epicenter was located. So these are the three records that we're going to look at, and we'll look at those together in just a second. And then we're going to record the information on this data table. So you should be able to see these things in your lab. So let's look at the first one. The first one is from Tibet, China. That's where the station was located that recorded the earthquake, and its nickname is IC.LSA. Just keep that in mind because you'll see that again. So they've shown you that this is the arrival of the P wave, and this is the arrival of the S wave. Now the P might have been obvious, but the S certainly wasn't because there's so much going on in here. And then our job is to figure out the time that those two waves arrived. And time is listed on the bottom in hours, minutes, and seconds. So this, for example, means it's 1:03 and 0 seconds and 1:04 and 0 seconds. And so between them, there are hatch marks, which means that each of these are 10-second intervals. So the time that the P wave arrived is 1:04 and 10, 20, 30 seconds. 1:04:30. So we're going to put that in our chart. The P wave arrival time at this station was 1:04:30. The S wave arrival time is 1:09, and this seems to be about halfway between those first two tick marks. So I'm going to say 1:09:05. And it looks like I've already run out of time, so we're going to continue this in the next video to figure out how do we figure out the difference between these two times. We need to take 1:09:05 and subtract 1:04:30. Well, that's a little tricky because time is base 60, right? There's 60 seconds in a minute, and there's 60 minutes in an hour. So it isn't just straight normal subtraction. And I'll let you think about that for a moment. And the next video will pick up with trying to figure this out.